back to hopefully the last part of our VAE autoencoders series. We're looking at the elbow, and we're gonna think about, okay, this term here, there's usually a closed form equivalent term, as in we can actually, like, if we set, remember, we usually set P to be some some normal distribution, some Gaussian distribution standard, and we can compute this KL divergence term. There's no issue with that. Here, right, there is an issue, right? Q of z of x, remember, is parametrized by this is your encoder. This is your encoder neural network, right? So what does it do? It takes in an x, right? And remember, it doesn't spit out just a z value, right? But it spits out, it outputs a mean and some sort of standard deviation or variance or whatever. By the way, I'm eating a popsicle while filming this, so if you ever hear that, you know why. Right? So Q of z given x, right? What we need to do to train this is we need to sample. Our whole idea is we want to sample from the latent space, right? But when we sample, it's a random sampling, right? Sampling z. So that the problem, okay, the key issue here is that when you look at this part, we're taking it over all the Q of z given x, right? We're randomly sampling z. Randomly sampling z. Okay? That's an issue. Why is this bad? Because randomly sampling is not a differentiable function. There's jumps, right? It jumps from one place to another at random times, and we can't predict that. So this is not smooth or differentiable, however you want to think about it. Which means we can't take the gradient and we can't do gradient descent, which is really bad. Okay, so we need to find a way, a nice trick, to be able to sort of externalize the randomness from our training. That's the idea. So right now, what are we doing? We have our, so let me clear. Right now, we have our encoder, which is Q of z given x, right? That takes in an x, so x goes into the encoder, and the encoder outputs a mean and a standard deviation. It gives us a distribution, right? Then, to sample, right, then z, okay, I'm putting a circle around it for a reason, you'll see. Z takes in these two parameters, correct? And it takes in these two parameters because it's sampling from Q of z given x, right? It's a random sample from there, and it gives us our output. It gives us a z that we then send to the decoder, right? And then the decoder will give us our x back. Okay, that's kind of what the pipeline looks like. Again, the problem is that we're going to back propagate through here, right? So we're going to back propagate through here, through here, through here. Also, back propagation is explained in one of my other videos, so go check that out. But here we're at a random. So circle here signifies a random spot, random node. So this is where random sampling is occurring, which is what we don't want. We don't want random sampling, at least in our back propagation. So how do we fix this issue? That's the question. What we do, okay, is we find a way of externalizing the randomness. So what I mean is, let's just think about a simple normal curve. Okay, so let's say our Q of z given x, right, looks something like this. Okay, so it has some mean mu and some standard deviation, whatever. Right? Standard deviation, variance, whatever. I use them interchangeably. They mean the same thing. One of them is squared, one of them's not. All right. Now, we want to sample from here. What we could do is we could realize that this curve is just a shifted and scaled version of the original standard bell curve, which has a mean of 0 and a standard deviation of 1. So this, right, mean of 0 and standard deviation of 1. Right? This is just a shifted version of this. So there's a nice rule in stats that says that the means will add. You can add to shift the means, and you can multiply to scale the standard deviations. So instead of sampling from this curve right here, we can sample from this curve and then just shift it. So what I mean is, instead of sampling z from here, we're going to sample what we call epsilon from a standard normal distribution. Okay? And then what are we going to do? We're going to take epsilon. We're going to scale it by the standard deviation. Correct? And then we're going to add. So I guess I should actually use standard deviation now. So not by the variance. Again, variance, standard deviation, whatever. We're going to scale it by the standard deviation and add the mean to get our actual z. So what we've done is we've taken this pipeline up here. Okay, now I'm going to rewrite it here, and you're going to see why this is very nice. We go x, we send it through the encoder, and we still get, remember our encoder is q of z given x, we still get a mu, and we still get a standard deviation. Let me actually fix this because it should be standard deviation, so I'll take you out. Okay, we still get a mean and a standard deviation. And these still are both going to go into z, correct? But notice how I'm not circling z, because it's not a random node anymore. The random node is actually going to be epsilon coming in through here, where epsilon is going to be sampled from a standard normal distribution, where we've taken our red, and then this also gets sent to the decoder. This gets sent to x. What we've done is, now when we back propagate, this function for z, right here before, z was a randomly sampled variable being sampled from this. Now z is just defined as standard deviation times epsilon plus mean. And so we can easily take the derivative of z with respect to any of these parameters, and we can optimize the parameters, right? So now back propagation nicely is able to flow through the network. And we don't care about this part, right? This part is not important to us. So we don't need to back propagate through there, and we can't because it's a random sampling. So what we've done is we've removed the randomness from our training algorithm. In reality, when we propagate forward, sure, we can randomly sample z. When we go backwards and we want to back propagate, we're going to have to externalize the randomness. And this trick, I probably should have introduced the name before, but it's called the Reparametrization Trick. Okay? Very nice trick. Again, we didn't go into the exact detail of how it works, but it's good to get an idea of why we need it, and why it's pretty smart, and how it allows us to, okay, instead of sampling from this actual, distribution we want, we do smart. We sample from a distribution, we can externalize the randomness, and then just shift over our whatever sample we get to fit our actual curve, the one that we want to sample from. Okay, so that wraps up VAEs. And yeah, hopefully you enjoyed.